just if someone asks something.
Right. Oh, I'm recording.
So we're recording? Okay. Can you see my screen okay, by the way?
Yes, yes.
Great. Okay. Yeah, so thanks for the intro again, and thanks everyone for coming. So today's talk is about how to use resets to make reinforcement learning more efficient. And it's joint work with Dylan Foster and Sasha Racklin. And we'll be presenting it later this year at NeurIPS. So let's start by looking at the current RL landscape. So when you look at the algorithms that people use in practice, they're often simple ones like PPO that are easy to implement and use. But the problem with these types of algorithms is that they typically do not come with any sample complexity guarantees. And in fact, they fail when the RL task needs more than basic exploration. And on the flip side, if you look at the algorithms studied in theory, well, they do come with sample complexity guarantees, which is great. But the issue is they either rely on unrealistic assumptions about the environment or the MDP, or sometimes they need to solve complicated optimization problems that are not tractable. And so this kind of highlights a big gap in our current understanding of how to design RL algorithms that are both sample efficient and computationally efficient. And actually, we don't even fully understand which MDPs allow for efficient RL. And so this is the gap we're aiming to address in this paper by focusing on RL with resets. So this is also known as RL with local access to the MDP. So local access is actually just one of at least 3 types of MDP access that has been explored in RL. On the one side, you have offline RL, where you have a fixed data set of trajectories or transitions, and the RL algorithm uses them to learn a good policy. And in this setup, the algorithm cannot interact with the environment to generate new trajectories. And on the other hand, there's online access, where the algorithm can interact with the environment to generate trajectories. And this is probably the most studied setting, both in theory and practice. Then the setting we focus on in this paper is this local access setting, which is far less studied. So in this local access setting, the algorithm can reset the state to any previously visited state and start generating transitions and trajectories from there. And so throughout the talk, I'll use the terms like local access or local simulator or resets to mean the same thing. And also I will say agent and algorithm interchangeably. So I'm assuming many of you would be more familiar maybe with the generative model or random access model, which is a model that allows resetting to any arbitrary state action pair. So obviously this is much stronger than local access because local access only allows you to reset to state action pairs that you visited in the past. So local access to MDPs is naturally available in many RL settings. So for example, in many RL benchmarks like Atari and Mojoko, local access is possible because the algorithm can simply save the state of the game and then reset it to that state at any point in the future. And local access is also available beyond these RL benchmarks, for example, in LLM applications, since you can reprocess any sequence of tokens that represent the states in this case, and then you can generate new tokens from there. And even though in the real world you can't always reset the state of a physical agent like a robot or a car, you can still reset. You can still use reset to train agents in a simulation. And actually, this approach has been used successfully in many real world applications. Whenever you have a high-quality simulation available. So as we just saw, like resets are available in many RL applications, but yeah, despite that, we still don't know much about what resets can actually bring in terms of sample and computational complexity in RL. And this is true from both empirical and theoretical standpoints. So on the empirical side, algorithms that leverage resets include, for example, AlphaGo or GoExplore. So AlphaGo is based on MTCS and famously beat the world champion in Go. And Go Explore was used in challenging Atari games that require exploration, like Montezuma Revenge. And he was able to beat the best human expert by a large margin. And although these results are promising for using resets, they're still quite limited. So for one, these algorithms typically only work for tabular environments. So you have to have like finite states. And in the case of AlphaGo, the algorithm isn't designed to handle stochastic environments and even needs resets during test time. So even though you can use resets in simulation, like for actual deployment in the real world, you don't necessarily have that ability to do resets. And so, yeah, and then you have on the theory side, resets have mostly been studied in linear functional. Anyway, so okay, on the theory side, you have people have mainly been studying resets in the linear functional approximation setup, and it's not clear how to extend those results and algorithms to the more realistic setting of general functional approximation. So in this work, we aim to fill this gap and get a better understanding of what resets can actually unlock. Specifically, we want to find out if we can design our algorithms for general function approximation that can provably benefit from local access. So I heard maybe there's a question.
Yeah, Anurav had a question, if I'm saying that right. Or maybe there's another accident.
Okay.
I don't see any hands raised anymore, so I guess we can just go ahead.
Okay, so here's the outline for the rest of the talk. First, I'll go into more detail about the RL setup and the MDPs we're going to focus on. Then I'll give an overview of the results. And the second and third parts will cover the efficient algorithms we develop that are provably efficient for a wide range of MDPs under local access. So let's dive into the RL setup. So we'll be working with episodic MDPs with Horizon H. So in each episode, the agent starts at some initial state, takes some action, and transitions to a new for H times. And from here on, I'll use the word layer to refer to a specific time step within the episode. The focus of the paper will be on value-based RL. Okay, so the focus here is on value-based RL. So we want to use function approximation to estimate the value functions, either for all possible policies pi or for just the optimal policy pi star. And specifically, we want to avoid using functional approximation to model transition dynamics, since the transition dynamics can be complex for many real-world application. Okay, with this in mind, our goal is to design value-based RL algorithms that make use of resets and are provably sample efficient and computation efficient. And so to do this, we'll need to first understand what MDP settings are tractable under local access. And so let's take a little bit of a step back here and see what MDP settings are tractable under online access. And when I say tractable here, I refer to like computationally tractable. So surprisingly, there are actually very few settings known to be computationally tractable under online access. And these include the tabular, linear, and low-rank MDPs. And although some of these algorithms are considered oracle efficient, they still require sometimes very complex optimization subroutines or oracles. So for example, in the low-rank MDP setting, the oracle involves solving a non-convex concave min-max problem. So this is not ideal. All these settings that I just mentioned that are somewhat tractable under online access belong to a broader class of MDPs with finite coverability. So if you're not familiar with coverability, so an MDP has finite coverability if there is some measure nu such that for all policies pi and for all state x, the ratio between the occupancy of x under pi, so this is the probability of reaching x under pi, over nu of x is bounded by some constant. Do we have a question?
Yeah. So Zach, so here when you define coverability, do you have a particular like policy class in mind, or this is literally for like all policies?
It's for all policies.
Okay.
Yeah. So was it Nan who asked the previous question?
Yeah, it was me.
The...
Yeah, it was me.
Okay. So yeah, this is for all policy spy, but I mean, it's still, there are many MDPs that fall under this category, as I'm going to show you in a second. Does that answer your question?
Yep.
Okay, cool. So, okay, one example of MDPs that fall under this category is exogenous block MDPs. So exogenous block MDPs are interesting because they can model many real-world applications. So in particular, exogenous block MDPs can handle applications where observations are high-dimensional, but there is some low-dimensional latent state. So for example, imagine you're trying to control a robot, trying to move it from some point A to B, and all you have are some images taken from some stationary camera. So in this case, you can model the latent space simply as a 2D map showing the robot's location and the destination. But the problem is that you don't necessarily have access to that latent state. Like the only input is the high dimensional observations. So what I just described was actually just like a block MDP, but an exogenous block MDP also accounts for exogenous variables. So like objects moving in the background that aren't affected by the agent's action. So in this example, you could have birds moving. And although these variables aren't influenced by the agent's actions, they still create a major challenge when it comes to learning the policy because they are part of the observations. So yeah, exogenous block MDPs are really, really challenging. And they are, they fall under, they do have a finite coverability. And all the existing algorithms that solve it in a sample efficient way, they make some strong assumption called completeness. So completeness is much stronger than just assuming that you can realize the value function. Yeah, so this is not ideal. And even if you have completeness, we don't know of any computationally efficient algorithm for this setting. So this is true more broadly for the coverability setting under online access. And in this paper, we show that this setting becomes indeed tractable, at least statistically, when you have local access. So this is one of our results. Okay, so before diving into the results, let's first compare the coverability assumption to other popular MDP assumptions studied in theory. So first, observe that all the MDP assumptions that I've just showed you, they kind of make some assumption on the dynamic. So they either assume something about the transitions or about the ratio of occupancies or something like that. But there are plenty of other MDP settings that instead of focusing on the dynamics, they rely on assumptions about the value functions or value function class. And this includes the linear settings, the finite Bellman eluder, bilinear classes, and so on. So how do these compare to the coverability assumption? Well, it turns out that there's an even bigger class of MDPs that is characterized by a finite sequential estimation coefficient. So I'm not going to give you the definition here, but the important thing to note here is that this class covers almost all the popular MDP settings. And the holy grail would be to develop a sample and oracle efficient for algorithm for this SEC setting. Okay, but since online RL algorithms are still stuck with low rank MDPs, aiming for this SEC setting seems pretty much out of reach for now. However, we might be able to achieve this with local access. And in fact, this actually turns out to be the case. So this leads me to the contributions. We have developed an algorithm called SimGolf that is sample efficient under coverability. The algorithm isn't computationally efficient because of it employs global optimism. And although technically we present the results only for coverability in this paper, they can be easily generalized to this finite SEC setting I just mentioned. And the second contribution is a more practical algorithm that works under another structural assumption called push-forward coverability. So push-forward coverability is a strengthening of coverability. And it pretty much includes all the settings that are already known to be tractable under online access. So yeah, this push-forward coverability covers all existing settings that are somewhat computationally tractable under online access, but also new settings like this weak correlated exogenous block MDPs, where the exogenous noise is somewhat weakly correlated over time. And just like it was possible to generalize the coverability setting to this more general SEC setting to include other value-based MDP assumptions, it is also possible to generalize push-forward coverability to include the linear function approximation settings. And our results and analysis can easily be extended to recover the positive results for the linear settings under local access. So to sum up, yeah, we have sort of like an oracle efficient algorithm for this push-forward SEC, and otherwise a sample efficient algorithm, but not computationally efficient for the SEC setting. So do you guys have any questions so far before I move on to the sample efficient algorithm?
So, so if I understand things correctly, your contribution, or at least the one that you're showing here, is that under this push-forward SEC condition that I guess you will show now, you have efficient algorithms for linear Q star and linear Q pi.
So, technically, the results of the paper, they concern push-forward coverability, which is like, part of this push-forward SEC. But as I said, like we can the analysis can easily be extended to this push-forward SEC to include, to recover the positive results for the linear Q star and linear Q pi. But the results for the linear Q star and linear Q pi, they are known because they are known under like the local access setting.
Right.
This is just saying that like we recovered those things.
Oh, I see. I see. Okay.
But I guess we do more than just recovering existing things, because we do have, we do also have like efficient algorithms for low rank MDPs, this weakly correlated exogenous block MDPs, and the oracles that we have are like just like involve solving some linear program over function space. So it's much better than what you have in the online access. Does that make sense?
All right. Yeah, sounds good. Let's do that. I'm ready.
All right. So let's look at the sample efficient algorithm for coverability. The algorithm is called SimGolf. It's a version of the golf algorithm, but with resets. And it uses the global optimism. And unfortunately, because of that, it's not necessarily computationally efficient. So here's the guarantee of SimGolf. Under realizability, if you have a function class that realizes the optimal value function Q star, and you have a finite coverability MDP, then as long as you choose the number of iterations t sufficiently large, then the algorithm can find an epsilon optimal policy. And the number of episodes is also polynomial in the problem parameters. And crucially here, we don't need completeness. So we only need realizability and a finite coverability. As I mentioned earlier, this result can easily be generalized to cover the finite SEC so that we can recover sample efficient results for Ballini classes and so on. And as a bonus, we show that you can use SimGolf to tackle the exogenous block MDP setting efficiently. So the coverability constants for exogenous block MDP is just bounded by the number of latent states times the number of actions. And so yeah, as long as you have a function class phi that captures the true decoder phi star in this setting. So in this setting, the true decoder phi star is a map that takes in observations to their latent state. So you don't need to know it, but as long as you have a function class that realizes it, then if you apply SimGolf, then you can find an epsilon optimal policy with a polynomial number of episodes. And this does not require any additional assumptions like completeness. Do we have a question?
Yeah, so what's the status of the setting in the usual online setting? Like, is it that we only know how to solve it if we have completeness?
Yes.
Oh, okay.
Yeah.
And I would guess simple golf is just replacing Bellman error estimation with a double sampling.
Exactly. Yeah.
Okay.
So the thing also that I want to, even if we have completeness, we still don't know how to solve it computationally efficiently. So in this work, as you will see later, we have something that's
efficient.
Yeah. Okay. Okay, you guys ready? Let's jump into the algorithm. So this is the simpler algorithm, and then for the oracle efficiency, it's a little bit more involved. But let's start with this one. So I'm going to show you a simplified version of the algorithm. In particular, whenever you see an expectation in what I present, just think of it as an empirical expectation. Okay, so the first step of the algorithm is to initialize some value function confidence set. So here, script Q is a function class that is assumed to contain the optimal state action value function. So next, there's a for loop over iterations. And at each iteration T, the algorithm solves an optimization problem jointly across all layers of the NDP. Then the solution of this problem is used to define the policy to execute for that iteration. So you just take the argmax of the value function. Okay, the next step involves updating the confidence set. So I'll explain more about the confidence set in the next slide, but for now, just note that this is my notation here for the Bellman operator. And finally, once you update the confidence set, the algorithm returns and finishes the iterations. The algorithm returns a policy from one of these policies across the T iterations uniformly at random. So this is just like golf, like it's slight variation of golf. So let's dissect the definition of the confidence set. So again, remember that.
First, can I have a question about how you? So if you go back to this previous slide, you write argmax over Q1 through H, which is in Qt, but what you're optimizing is just Q1. So I suppose like Q here means like so Q1 through H.
No, like
functions that are defined.
So the convex set here includes all the Q1 to QH, right? Even though that's why you have like all of them here. Even though the objective only has Q1, the others are involved in the constraints.
I see. So you're not free to choose like the Qs for each H, for each index H, but you have to choose like an entire sequence that is somehow coherent.
Yeah, because you have they're entangled, right? So you have a Q1 will appear here, like it will involve Q2 as well, and so on. So
right.
They're not. They're not. It's not like a separable objective.
Yes.
Yeah. In fact, this template is the same as the original golf, right?
Exactly. So I mean, the only difference is the way we will we define the confidence set. So here, because we have resets, as I'm going to explain in the next slide, you can estimate the Bellman operator directly, and you don't have any double sampling problem. But I'm going to show you this in the next slide. Does that answer the question?
Yes, absolutely. Okay. Thank you.
Okay, so yeah, as I said, like remember that so technically this confidence set needs to be defined using empirical expectations, not population expectations. And also, in particular, in this expression of the Bellman operator. So the Bellman operator involves this conditional expectation. And unfortunately, in the online setting, estimating this quantity, which is required to define this confidence set, is not possible without completeness. This is known as the double sampling problem. And so, yeah, the reason we get away with it here is that local access allows us to estimate this quantity. We can just reset the state to XA and generate multiple next states, and then you can just do an empirical average to estimate this quantity. So this is the key observation that allows us to tackle the coverability setting under realizability alone without requiring completeness. Okay, so yeah, finally, you have like same as golf, you set the threshold here in a way so that the confidence set would include the optimal value function Q star. And this in turn ensures that we maintain optimism in the sense that the optimal value of this objective in this optimization step is an upper bound on the value of the optimal policy pi star, right? Okay, so that's roughly how the algorithm works. One thing I would add here is that because the Bellman operator has a max over actions, this confidence set is not convex in function space. And so because it's not convex, it's also a reason why this algorithm is not computationally tractable. Okay, so now we're going to if you don't have any questions, I'll move on to tell you about the more practical algorithm that operates under the slightly stronger MDP assumption. Any questions at this level?
Is that the only reason why this algorithm is not computationally feasible? Like, you also have to compute this version space, right? Or are you saying you have some set of constraints and you do some kind of like optimization over it?
Yeah, the constraints are, I mean, it's the fact that the constraints are non-convex that's the problem. But
sure, okay.
So yeah, it's precisely because of the non-convexity of the constraint. Yeah.
I guess, has anyone really established anything like computation intractability, like even when things like are linear?
So
I guess it's always like seems to me like a folklore that we don't know how to solve it, and I suspect that it will be hard, but probably there is no hard results formally.
I'll say a couple of things. So for Olive, which is also an algorithm that's based on global optimism, you do have lower bounds that show you that you cannot implement it in an Oracle efficient way for most.
Yeah, I was on that piece.
Yeah. Okay. So I guess for golf, it's a little bit more tricky to extend that result. Right. I mean, I've personally thought about it in the context of, like, for example, the linear Bellman complete setting, where you have the feature map, and even then, like, it's really not clear.
Yeah. So I guess there's an open question sort of there.
That's true. Yeah. Yeah. Okay. So okay. Any other questions before I move on to the last part? Okay. Okay, so the algorithm for this part is RVFS, which is provably efficient under push-forward coverability. So push-forward coverability, as I said, is a strengthening of regular coverability. It asserts that there is some measure nu such that for all state action pairs XA and for all next states X prime, the ratio between the transition probability to X prime from XA over nu of X prime is bounded by some constant. So the difference between coverability and push-forward coverability is that you replace this. Before we had the ratio of occupancies, now we have the ratio of this transition. And obviously, if you have push-forward coverability, that also implies finite coverability. So as I mentioned earlier, this includes all the settings that are known to be computationally tractable in RL, in online RL, and it also covers new settings like a version of the exogenous block MDP where the exogenous noise is only weakly correlated over time. Okay, so RVFS stands for recursive value function search. It is both sample and Oracle efficient and only requires either VPi realizability for all pi or V star realizability with the gap. And as we'll see, the Oracle involves solving a convex programming function space, which is much simpler than other existing oracles in online RL. So one key feature of this algorithm is that it maintains a core set of state action pairs. So essentially, whenever the algorithm comes across some state action pair that seems very different from the ones it's seen before, it will add it to a core set. And so in the tabular setting, you can just add any new state action pair that hasn't been encountered to this core set. And this is actually what's done in, for example, AlphaGo. In the linear function approximation setup, when you're given some feature map phi, existing approaches typically measure the uncertainty of a state action pair using some elliptical objective. So in this paper, we go beyond the linear setup because we're considering this push-forward coverability, which generalizes the linear setup. And so one of the challenges we had to overcome is how to generalize this concept of uncertain state action pair beyond the tabular and linear setups. And finally, the recursive nature of RVFS is somewhat similar to the recursive surge used in MCTS. But unlike MCTS, which typically only works for the tabular environments, RVFS come with provable guarantees that extend beyond tabular and linear. Okay, before I walk you through the algorithm, let's first look at the guarantee. So now we work with V realizability instead of Q realizability. So given V pi realizability for all pi and push forward coverability, RVFS can compute a near optimal policy and it does it with a number of samples that is polynomial in all the relevant problem parameters. And so here the V pi realizability can also be replaced by V star plus a gap instead. And the algorithm is oracle efficient, and the results can be generalized to this broader class of complexity measure that recovers existing results in the linear functional approximation setup. So maybe I'll pause here just like for a minute if there's any questions about the guarantee before I move on to the algorithm.
So when you say that RVFS returns pi hat induced by V hat 1 through H, so what does that exactly mean? That the policy is induced by a value function class?
You will see it in the next slide.
Okay, right. Because that's the only cryptic part that.
Good catch. Good catch.
Here.
Any other question? Yeah, because typically, the policies are induced by Q functions because you take the R max, but like a V doesn't have, it's just a function of the state. So yeah, that was a good question. So that's going to become clearer when we go through the algorithm.
All right.
Okay, so RVFS makes recursive calls to itself. So let's just focus on a call at layer H. So disclaimer, I'm going to show you a very simplified version of the algorithm just to highlight the key ideas. So the algorithm takes in as input some estimated value functions for future layers, and it also takes in confidence sets for future layers and core sets. And so intuitively here, core sets, because I didn't mention it before, core sets are state action pairs from which you will be doing rollouts to refine your estimates of the value function. That's intuitively what's happening here. Epsilon here represent the desired level of suboptimality. Okay, so the first step of the algorithm involves a loop over state action pairs in the core set of layer H, and also a backward loop over future layers. So that's L in red. Then, okay, given this state action pair in blue, the algorithm rolls out using pi hat. So, hopefully this answers the question that you asked. So the policy here is somewhat unusual because it involves computing the Bellman operator of the estimated value function to get the actions to execute. And so, yeah, this is somewhat unusual, but we can actually compute these policies because we have the resets. So we can just reset to any state action pair, sample the next state, and that will allow us to estimate this quantity here. And actually, this choice of policies turned out to be crucial in the analysis. So initially, we tried with the more common approach of using policies that are induced by Q functions like SimGolf, but that actually led to errors blowing up with the horizon of the NDP. Okay, so you sample those state action pairs in red. So now that you sample this state action pair in red, the next step is to check if the state action pair is novel enough to be added to the core set. And we do this by solving this optimization problem that I have here on the third line. And so the quantities you see here in this objective are, again, Bellman operators, which can be estimated efficiently using resets. And the function here, f, over which you're optimizing, varies over the confidence set for layer L. So as we will see, unlike in SimGolf, the confidence sets that we have here in RVFS are actually convex. And so basically this allows us to reduce this optimization problem to two linear optimization problems over function space that is convex. And so you can see here that there's it's a supremum of an absolute value, but you can actually just solve two problems with plus and minus. And that basically reduces to a linear program because the Bellman operator is linear in the function f. So if the objective is linear in the function f, and the confidence set is convex, this is just a convex program, a linear program over function space. Do you have a question about this?
Yeah, I mean, I can see how it's linear if you directly linearly parameterize the v value function, but You also mentioned some setting of like Q function approximation. In that case, isn't that a little bit tricky?
Well, so here we are working with VPy realizability. So like we have
okay.
class that
Okay, got it.
Yeah. But yeah, if you have Q, then you have like the max that causes problem again.
Right. Okay.
Yeah. Okay. So any other question on this objective and why it's linear? Just from the definition of the Bellman operator, it just involves an expectation, so that's linear in F. Okay, so
I have a question. So compared with your previous algorithm called SimGolf, it seems like you just changed the square into the absolute value. That's the main change that results to convexity. Yes, I'm just not sure.
Well, in SimGolf, the square was actually hidden in the confidence set. So we will have a square as well in the confidence set. So the objective that we had in SimGolf, it was actually also it was maximizing an expectation of like Q function. The difference to this is that we had the max over actions there, and here we don't have a max over actions. And like the bigger difference is the confidence set is actually convex in our setting. I haven't showed you the confidence set yet, but that will become a little bit clearer in a second.
Okay, thank you. Yeah.
Okay, so also remember that like when I mentioned that it was unclear how to generalize this notion of uncertain state action pairs beyond the linear setting. Well, this is one approach at least that leads to provable guarantees. So you solve this convex program over the confidence set. So if the state action,
maybe just one more question. So like so here you just sample a single state action pair, and then you do this check for that state action pair, and that's it? Or you do this a bunch of times?
In the actual algorithm, you sample a bunch of these, like not just one. I just did it here for one just to simplify the presentation.
All right, okay.
The actual algorithm, like you sample like n, and like you choose n based on some based on.
And when you talk about the convexity of this problem, I guess, or the linearity of this problem, it's because you're doing this check for like single state action pairs and not with respect to like some distribution.
Exactly.
Right. Okay. Got it.
Okay. So if you do this check and this objective is greater than epsilon, then you deem that state action pair to be novel or uncertain, and then you add it to the core set. And once you add it to the core set, then you call RVFS again at that layer where you've encountered a new state action pair. And so, okay, if you do this for loop and you haven't found any state action pair that was novel, then basically you just re-estimate your value function. So you do rollouts starting from state action pairs in the core set, and you fit this value function VPy hat. Okay, we're almost there's only 2 lines before we finish this algorithm. So like just hang on. So once you have this V hat, now we get to the point where we can update the confidence set. So the confidence set here is simply defined as the set of functions that are at a small distance from this estimated value function V hat, right? And in the actual algorithm, the conditional expectation is estimated using resets from xh-1 and ah-1. So just to come back to the point earlier, like we do have the squares in the confidence set, but the difference here is that we don't have the Bellman operator that has the max over A that makes things non-convex. So yeah, this is indeed convex, which is nice from a computational standpoint. Do you have any questions about the confidence set?
I think it seems like you just replaced the Bellman. Okay, so previously in SimGolf, you just have a Bellman with max A. Then now you just replace it with the V hat. Yes. Yeah.
I mean, in a sense, yes, we are replacing Q functions by the value functions. But there's more to it than just that. Like I think if you go to golf and try to do this trick, it will not work because you do need the Q function and you do need the max over A. So you cannot just swap everything to V functions and everything will be good. Yeah. So that does not work there.
Okay, thanks.
Okay, so we are here now. Now this is then after this is just the final step where the algorithm returns the updated estimated value functions and confidence sets. So to come back to Gerge's question at the beginning, when I said policies induced by pi, so here, look, this is RVFS for layer H, but the first RVFS that you're gonna call is RVFS at layer 1, which gonna call the subsequent RVFS. But once RVFS 1 is gonna return, it's gonna return the set of the V hat 1 until H, and you're gonna define the policy based on that using this like Bellman. You're gonna define the policies this way, right? Does that make sense?
Yes, that does make sense. Right.
So there's a subtlety here, however. So to compute this policy, you need resets. And I did mention before that like one of the drawbacks of, say, AlphaGo was that you require resets at test time, which is not ideal. So if you were to deploy this policy, well, you will require resets at test time because otherwise you're not going to be able to estimate this. So what we actually do in the paper is that there's another algorithm after this that just does behavior cloning. And so you can, you input this expert policy and you just do behavior cloning to learn another policy that you can then deploy without having to do resets. So that's like a subtlety that I didn't include here in the slides. Does that make sense?
Right, yeah.
Yeah.
Yeah, so then I guess I wonder about like the overall sample complexity. I mean, I worry that it's going to be some horrible polynomial of 1 over epsilon, no?
I mean, sure, but I guess that's the case in RL in general.
Right, yeah, true.
I mean, it might not be that horrible, but yeah. Okay.
Right, yeah, because I guess like every time you calculate such an argmax, you need to take like at least like 1 over epsilon squared.
Yeah.
Gross simulator, and then I guess also in this optimization problem, you're facing this problem, right? So
the main issue here is that if we were doing it for a single state action pair, this would be fine. But the fact that we're doing it for many of them, that's definitely a drawback. So we're trying to sort of see how we can improve this. But yeah, you're on point.
Right. Well, I guess it works, so that's good.
Okay, so
so before we move on, I have a quick question about using the the V induced policy versus Q. I'm guessing is that because if you use the Q based policy, like you get when you have error accumulation, you get a constant multiplier that is greater than 1.
There's something like that happening in the analysis.
Yeah. It just reminded me, like I think I remember, like when we analyze algorithm like this, sometimes the per level error actually like constant matters like a lot there. Like if you get a multiplier of 1, like it's linear accumulation. If you get anything greater than constant greater than 1, like if it's factor of 2, then 2 to the h.
Yes, I agree, and I think it's in the analysis it's like very subtle, like where it comes up. But yeah, it seems like you have to do this like one step back and take the Bellman operator somehow. Okay, I'm close to the end anyway, and then you can take more questions. So I wanted to sum up. I just showed you RVFS, which is a sample and Oracle efficient algorithm for the push forward coverability setting, and you can extend it to this SEC and under local access, of course. And then we have the sample efficient algorithm SimGolf for the general coverability setting, but it's not computationally efficient. So to wrap up, here are the main takeaways. So resets make many more MDPs tractable compared to the online RL. And this opens up new avenues for applying RL. The other novel thing is we introduced a new uncertainty measure for state action pairs that goes beyond tabular and linear setups, right? So this is very important, like because if you want to generalize this algorithm like AlphaGo and all these things beyond the tabular and linear setups, this kind of gives something that's provably working beyond these settings. And you can think of like the RVFS as a more principled version of MCTS, if you like. So the big question that remains here is you know, can we develop some Oral coefficient algorithm for this most general setup that of coverability or SEC? And yeah, on the empirical side, I think there's definitely some new ideas that haven't been explored much, and so this could be good to do for future work. And yeah, so I'm happy to take any questions now.
All right, cool. Thank you. Very nice. So, people can think about their questions, but while they're doing that, I have a question regarding like the role of this push forward coverability assumption. So where does that actually appear in the analysis? Because I guess I sort of missed that part, because yeah, I mean, I understand the algorithm and the components and the results, but like, why was this push forward coverability thing required?
Okay, let's see. So push, like in a nutshell. So see here how I said, whenever you have a state action pair that is that has like a large threshold, then you add this state action pair to the core set.
Mm-hmm.
Essentially, since this test involves, you know, going one step back and taking the Bellman operator, it push forward coverability guarantees that you will not fail this test too many times. Because if you fail this test too many times, then the algorithm will never terminate. Like, it will just keep calling like the RVFS. So push forward coverability ensures that like you will basically cover all, like eventually all like next state directions. So that's where it comes in, essentially. Like it just guarantees that the test will not fail many times.
Yeah, I guess the other way to put it is that because you have push forward coverability, it allows you to do this test in a per state action manner, right? Because otherwise, it probably only makes sense to do it in a, you know, distributional manner, but not allowing you to zoom into a single state action.
Sure. Yeah, exactly. And so like, yeah, the point is like there's only finite number of times that you can actually fail this test because of push forward coverability. So that's, I guess, the rough explanation that I would give you here.
Right, got it.
And if you didn't have the Bellman operators, then if you just had like, you know, you wanted to test XA directly on F and V hat, then you may fail this test like, you know, an infinite number of times. Like, nothing guarantees that you will eventually stop. So the fact that you go one step back is precisely to guarantee that you will stop eventually. Yeah, and like naturally this goes hand in hand with the way we define the policies as well, by going like one step back.
Right, cool. So there was another question in the chat. Edward was asking a question. I don't know if you can ask.
Sure. Zach, I had a quick question about adding entropy regularization here, if it would help in terms of sampling from pi hat, because you might be able to get a sort of a closed form depending on your V, at least something that you can sample, something like a soft max that depends on the value function approximators that you're using.
And so you're wondering if this would help in terms of what?
In terms of the sampling pairs of state action pairs in pi hat.
Okay, instead of like estimating the Bellman operator, you mean? Or
yeah, exactly.
I see. I haven't thought about that. I did, however, think about, you know, considering this like regularized setups in the context of you know, LLM applications. And the idea there would be to come up with an efficient algorithm using some of these RVFS ideas. But I haven't, like, outside that context of like, you know, using this regularization just to get an efficient sampling, that one I have not thought too much about it yet, to be honest.
It might also help with the convexification as well of the problem.
I mean, it's already convex in function space here, like the problem you're solving here.
Gotcha.
Right. Yeah. So yeah, the question might be, that one might be more maybe relevant to SimGolf, like if you use this entropy regularization, if it makes things more convex. But actually, there's this paper by Dylan Foster and other people who they have a version of SimGolf of golf that uses entropy regularization, and it's not quite convex yet. So it's still open whether you can modify it in a way that makes it amenable to implementation.
Gotcha. Thank you for that.
Thanks.
Yeah, so just ask. So, you know, I mentioned in the chat. So Chapa and Tor and collaborators, they also have some work on MCTS using core sets, right? I guess they have a different definition of core sets. I think if I remember correctly, it's like in the linear setting where all other state action pairs features are convex combinations of features on the core set or something like that.
So which paper are you referring to? Exactly?
It's they have a sequence of papers that like many use this definition. So, I mean, I guess your definition is quite different, but well, it's not that different. I think it's definitely like it's different, but definitely related. So maybe I think it's maybe a good idea to look it up and see, you know, what's the connection? Can your algorithm? You know, it would be nice, like for example, if you take their assumptions and ask like, does your algorithm maybe like for example apply that? Because in their setting, not only they need to make that assumption that the number of state action pairs in the core set is small, because in general it can be like exponential, right? Because essentially you need the core set of state action pairs to put their features to create like convex hull like of all the state action features. Not only they require it to be polynomial, according to my memory, they also need that set to be known to the learner. If I
right, man. If I may jump in,
yeah,
because
like maybe there's some hope that if you directly apply your algorithm in their setting, you can avoid like knowing that core set to begin with.
So then I think I know what you're talking about, but I think that their terminology is kind of confusing because they had some papers where they made this assumption that there's a small number of states such that the features, like the convex combination of the features in the core set generate all the possible feature sets. But then they had some follow-up papers where they used the same word to denote like a different set of state action pairs with a different property. And there, the property was very similar to what Zach has here. So they add new state action pairs to the core set every time that this kind of elliptical potential thing is large. So the thing that you remember, so that is like a different notion of core sets that that eventually did not make an appearance in their later papers.
Right. I mean, yeah. I mean, I'm vaguely familiar with that paper that you mentioned, but yeah. I mean, I haven't looked into like whether we can use some of these tricks to remove that assumption. But I think I chatted with Chaba. Like I think the how to generalize this notion of uncertain state action pair beyond linear setup where you have this elliptical objective is kind of like it was not clear until I guess this paper offers one way of doing it.
Yeah. I think it would be cool if you examine that, right? For example, if you assume that their definition of core set has a small size, does your, like maybe if you can show that your algorithm will automatically discover a set that is not much larger than their definition, then I think likely means that your algorithm can be applied to their setting.
Okay, well, I'll definitely look into that paper and maybe we can chat.
Yeah.
So Jean had a question. I don't know if you're still here. Oh, okay. So Jean says that he cannot unmute. So let me just read his question then. So Jean Lee was asking, are there any settings for which push forward is important for sample complexity if I don't care about computational complexity? Like a setting where we don't know if coverability is sufficient, but with push forward, we have a statistically efficient algorithm. And he says that BVFT is an example. BVFT, I don't know what that stands for.
Can you just like summarize maybe the question again?
No. I'm also just reading this on the fly. So I guess what he's asking is for some kind of like a separation that says that coverability is sufficient,
No, push forward works, but only having coverability doesn't work statistically. Or track by working,
okay.
I mean like tractable.
Oh, so you want to show a separation where, you know, we have a setting where you can tackle the push forward coverability efficiently, but not push. You can tackle push forward, but not coverability.
Yeah, I think that's
Right.
essentially what he is asking.
I think this space is lacking lower bounds for sure. So like we you know, at least we know that things are statistically tractable even for the coverability setting. At least in this local reset setting, as we saw. But I don't think there's any lower bounds for, you know, showing that you cannot be Oracle efficient for coverability, right? So this work shows that you can be both Oracle and sample efficient for push forward coverability. And beyond that, that's still an open question. And I'm very much interested in that. So yeah, then we don't know. I would say though that for in the offline setting, I think there are lower bounds in the online access setting that shows that something like coverability is not sufficient for, you know, you cannot solve it computationally efficiently.
Well, no, but in that case, it's just coverage, not coverability. Right? Coverability
Sure. Yeah.
yeah. Version of coverage.
Yeah. But yeah, beyond the offline setting, it's not clear.
All right, so if there are no more questions, then maybe we can go off the record and we can go like more technical. If